Hi everyone, my name is Amélie Gruel. I'm a third year PhD student at IEEE CNRS, and today I will be presenting you our work on simultaneous neuromorphic selection of multiple salient objects for event vision. This work has been done in collaboration with my supervisor, Jean Martinet, and Michele and Magno, researchers at ETH Zürich. First of all, I'm going to tell you a bit more about the different neuromorphic materials that we use during this work. The first one is the event-based camera, also called dynamic vision sensor. This camera is bio-inspired and only activates or produces events, on-off activations at each pixel if and only if there is a change of luminosity at this pixel. This produces data that is both very sparse and requires low memory to be processed and low energy consumption to be recorded. This kind of data is particularly suited to be handled and processed by a new kind of neural network, which is spiking neural network. This kind of neural network is bio-inspired and handles data not at floating point numbers, but as trains of spikes. This kind of spiking neural network is really interesting for embedded systems, especially because it can be implemented on neuromorphic hardware that is specialized to implement this kind of neural network and simulate them at a low power costs. I just told you that event-based data is quite sparse, so why should we want to reduce it? Because this is actually what we are going to do in this work. We are going to try to see how can we reduce event data. An embedded event camera will record events that is both produced by the event in the visual scene, but also by the ego motion of the UAV on where it is embedded, thus producing a lot of events, sometimes too much to be handled in real time, which is what is required for embedded system. So different methods to try to reduce this event data on an embedded system have been introduced, either neuromorphic or non-neuromorphic in our previous works, but these different methods are not optimal. And we believe that this is the case because those methods just reduce the spatial resolution of the event sensor without taking into account the interesting elements of the visual scene. We do not keep any information on where it is more salient, more visually interesting. We just don't scale everything without any difference. So what we're going to do now is that we're going to introduce this concept of visual saliency. We are going to select and process objects of interest only in the visual scene. So how are we going to do that? Well, we are going to take inspiration from a reference model, which is a model that we published at ICAST 2022, that produces neuromorphic visual attention for object of interest selection. This model originally was selecting only one object of interest at a time. So we built on that in order to select multiple objects of interest at a time. Let's just take a look first at this first model. So as you can see here, it is quite simple. It is composed of only 3 spiking layers that are connected together with 2 sets of synaptic connection and that are overruled by 2 adaptation rules. The saliency detector layer detects the saliency using a soft exponential winner-takes-all that clusters the different salient elements together in order to detect regions of interest in the visual scene. This is reinforced by the weight adaptation rules. A second rule is a rule of the threshold adaptation. What it means is that if the saliency detector detects an activity in the input sensor, meaning that it detects events that are salient, so salient elements in the visual scene, it is going to decrease the thresholds of the neurons at the corresponding region in the output layer. What does that mean? It means that this way the events that correspond to this region will be facilitated to spike. At the contrary, if there is nothing that is interesting in the regions corresponding according to saliency detectors, then we are going to increase the corresponding threshold in the corresponding neurons of the output layer in order to inhibit the activity. First, we're going to experimentally validate this first model further than what was already done. So in order to experimentally validate this model and the one that we're going to introduce, we use the DVS 128 gesture dataset, which is a basic dataset in event camera processing and neuromorphic hardware in general. We believe that this dataset is a good idea to be used for neuromorphic visual attention, because if we select only the object of interest in a scene, we are going to select only the hands, and if we just keep the hands, we are able to recognize the movement, so the hand gesture. Additionally, we use different samples of the DVS 128 gesture in order to create some custom-made datasets. Indeed, we were looking for dataset with event-based data, where we knew the global location in space and in time of different hand movements, or just objects of interest in general, and a way to classify them when we get only this object of interest. This is not a common thing in event-based dataset, because there are not a lot of them and it's really specific task. So what we did is that we took different samples of the DVS 128 gesture by keeping the labels of the samples and combined them 2 by 2 in order to be able to see how our models will react with different kind of combinations. So we have a first type of combination. It's a control dataset. We have twice the same movement in order to see which movement it will detect first. Does it depends on the timing of the beginning of the movement, maybe on the amount of events, and in order to assess this, we are also going to take a look at the random symmetric dataset, where we choose randomly 2 different hand movements that we are going to combine symmetrically, meaning that if we have a sample with one movement on the left and another one on the right, then we are going to have a second sample where the movements are interchanged. Additionally, we are going to use a temporal shift between the 2 samples that we used that range between 0 to 500 microseconds in order to assess whether the timing of the beginning of the movement has an impact or not on the detection of what is salient. As I said, we are going to first validate the selection of one object of interest with our previous model in order to make sure that it is interesting to continue building on it. So here we have qualitative results first. So you can see here that we took the same samples that are presented to you earlier, and we gave it as input to our neuromorphic model. As you can see here, we did manage to detect only one object of interest that is really localized in space and in time. Another way to assess the quality of this selection of one object of interest, we took a look at the percentage of activated surface and the width and height of the activated surface post-treatment. So you can see here on the first one that we have only 0.1% of the surface that is activated post-treatment. So that is really interesting because we wanted to decrease the number of events, and this proves that it did that. And we also reduce the surface to be handled by and processed by our spiking neural network. Additionally, we use the output of our model in order to classify the movement that we get with this output. So the model outputs an object that corresponds to the hands of the different samples, and we put those hands and the temporal pattern that they make in a classifier that was originally trained on the original DVS 128 gesture dataset. As you can see here, in average, we managed to keep 73% of the original classification accuracy, which is pretty good. Now I'm going to tell you a bit more about our contributions, so the simultaneous selection of multiple objects of interest at the time. As you can see here, we built on the original neuromorphic model that I presented to you earlier to build a new one. Here in this architecture, I will present in the following presentation, I will only tell you about the simultaneous selection of 2 objects of interest at a time in an effort to be more comprehensible. However, theoretically, this model could be implemented with an unbounded number of objects of interest to be detected, so an unbounded number of output layers, with the slight issue that if you add output layers and you add neurons, and you add also one-to-one connections between the input and those output layers, so it adds to the complexity of the model, and you will also have to add additional threshold adaptation rules and lateral threshold adaptation rules that I will tell you a bit more later. Let's take a look at how it works. So on the saliency detector part and weight adaptation rule, we are keeping the same mechanism that we implemented in 2022, but we updated the threshold adaptation rule. Instead of only relying on the activated region identified by the saliency detector, we are going to additionally have a complete memory of all the activity in all the layers in order to not let through the object of interest that happened and were already let through by a first output layer in the second output layer. If we take a look at our experimental validation for this model, so we took once again the two samples that I presented you earlier. As you can see here, we managed on these two samples to identify simultaneously two objects of interest that are output by the model at the same time. Now we can take a closer look at the quantitative quality of our model according to the temporal shift between the two objects of interest that we wanted to detect. So as you can see here in the first figure, the performance of multi-object detection reaches at most 15%, meaning that 50% of the time at most we are able to simultaneously detect two objects of interest. This performance actually decrease with the time shift. This is still something that we are working on, but this is our first result for this model, and we still managed to reach 50% of the time, which is better than was done before. And we believe with the other information I'm going to tell you about that this is still an interesting way to go, and it just needs to continue working on the hyperparameterization of the model. As you can see on the second figure, we did assess the detection latency according to the shifts in the two objects of interest. So the detection latency is the time that it took for our model to detect an object of interest in the input. As you can see, it reaches at most 15 milliseconds, which is quite quick and really interesting for embedded application. Finally, we also took a look at the classification accuracy of the selected objects of interest that were output by our model. And as you can see here, this object of interest managed to keep a quality that corresponds to a classification accuracy that does not fall below 75% of the quality of classification. Compared to a baseline of 92%, that is the baseline of the original classifier on the original dataset. Now we will compare our contribution to the rest of the state of the art. We choose two previous articles that implement a neuromorphic model of visual attention on event-based data. The two models are the ones implemented by Renner and colleagues in 2019 and D'Angelo and colleagues in 2022. We compared the saliency detection, so only the input layer and the saliency detector in terms of number of layers, number of neurons, and number of synapses with those other models, because the other models do not perform a selection of objects of interest. So the first 4 lines correspond only to this, and later we'll see a more complete comparison. So if we only take a look at the saliency detection part of our model, with our contributions, we managed to have similar or better than state-of-the-art number of layers, better than state-of-the-art in terms of number of neurons that we use to implement, and finally the number of synapses is in the average. So it is quite promising. And additionally, we also, in our two models, offer behavior and function that are not provided by the two previous state-of-the-art models that we identified. With our initial model from 2022 and our current contribution, we managed to select object of interest, and additionally, in our current contribution, we propose a model that is able to select simultaneously multiple objects of interest at the same time, and to the best of our knowledge, we are the only people that do that. All in all, as I said previously, we are the first neuromorphic model able to simultaneously select multiple objects of interest in an event scene. Even though, as I told you, we still require an additional hyperparameterization phases in order to optimize our model, this is all in all quite promising. Our future works include validating this model on greater event datasets, such as the 1 megapixel detection dataset that was recently published. Additionally, we want to validate this model on an increasing number of objects of interest, so adding an increasing number of output layers. And finally, we would like to implement and validate this model on neuromorphic hardware such as Spinnaker, Kraken, and data interface with an event-based camera in order to demonstrate the use of this model on an embedded UAV. Overall, We believe in the usefulness of this model in embedded multi-object tracking or SEN segmentation. I am available to answer any question you might have, and I would like to thank you very much for your attention.